Hello and welcome to my talk on computational parquetry, fabricated style transfer with wood pixels. I am Matthias Hullin, and this work was done together with 3 colleagues at the University of Bonn. In this paper, we are revisiting marquetry or parquetry, which is the art of arranging pieces cut from materials such as wood, stone or metal. Here we see a still life from Italy around the 15th century AD, but the origins of this art form date back much further than that. Some examples show floral and geometric ornaments, while others depict humans and animals. The amount of detail invested can vary drastically from one example to another. This one here is really detailed, while this one uses very simple cuts as a stylistic device. We can think of traditional parquetry a bit like painting by numbers. You segment the image, think of suitable materials for each segment, and then cut and assemble. What now if we want the outcome to look more like a photo? Well, we can make the technique more realistic by using more kinds of wood and making finer cuts. This is as far as artists have pushed it. If you have a really steady hand and if you're willing to invest the time for it, you can reach amazing levels of detail and artistic expression. At the same time, however, we want to get by on a manageable number of pieces. What we see here in this ancient mosaic is exactly what we do not want. Selecting, cutting, and fabricating tens of thousands of little pixels is just intractable. When working with natural materials, there are severe constraints to what we can do. If we're given a piece of material, we can cut it into smaller pieces, and that's it. We cannot stretch it, we cannot copy it, we cannot filter it, we cannot change its color, we cannot blend it, and we cannot do any fancy multi-scale tricks with it, and so on and so forth. So, out of the space of all imaginable computational tricks, only a small subset applies to our problem. Of course, being computer folks, we want to have the least amount of manual labor involved. Here, the artist used computer software to posterize the gray levels of the input photograph. From then on, it was all tedious manual labor, sketching and cutting and gluing hundreds of really oddly shaped parts. We want to generate patterns that a CNC device can cut out. Our key to making many of these points possible is that natural materials are rich in variation and detail. Here, for instance, is an arrangement of different types of wood veneer. If we chop these woods into little pixels, we see a large variety in structure and intensity. So much so that we almost don't notice that only 50% of these squares is actually wood. The other 50% are taken from this Ludwig van Beethoven portrait. Apparently, when we cut wood into little chunks, it is easy to confuse with other things. So now, if we can take bits of Beethoven to stand in for our wood, we can also do the opposite and build something that looks like Beethoven, but consists entirely out of wood pieces that aren't even all that small. And that's what our work is about, a new kind of computational parquetry that exploits the rich and varied structure found in natural materials to produce one-of-a-kind, detailed renditions of a target image. Another way of thinking about this is as stylization in the real world. So what does the state of the art have to offer? There has obviously been a lot of great work on rendering image X in the style of Y, and more amazing methods are coming out almost on a daily basis. They are mostly based on deep learning nowadays. But what happens when we want to have this cat in the style of zebra wood? Well, deep style transfer doesn't really get the concept of wood. And what's worse, it can't respect the fabrication-specific constraints. In contrast, we want something like this. We want to obtain renditions that globally approximate the target image, yet locally are clearly wood. This means that we have to go back to patch-based synthesis. But not every approach will work for us. Again, we can cut, but we can't copy, stretch, filter, and so forth. Not being able to do all these operations means that even within the realm of patch-based synthesis techniques, we're essentially stuck to the state-of-the-art as per 20 years ago, because all the bells and whistles that have been invented since don't apply to our problem. So, at the core, our algorithm is really just a primitive patch matcher that for a given region in the target image finds the best matching piece of wood. However, there are a couple of small things to consider when trying to implement a design and fabrication pipeline around that. So we may have to take another closer look at a few task-specific challenges. Let's start with an overview of our pipeline. We start by scanning panels that contain one or more types of real wood veneer. Using a target image and the scans as input, we run our algorithmic design pipeline to generate a cut pattern for the computational wood puzzle. The cut pattern is executed by a laser cutter to fabricate the individual puzzle pieces. Finally, the puzzle pieces are assembled, fixed, and a finish is applied. A central question that we are going to have to think about is by what distance metric we're going to do the matching. First, however, we note that target and source image can be quite different in their color gamuts. Without appropriate measures, it will be hard to find meaningful matches. When matching histograms separately per color channel, we're sometimes in for a surprise, like here, where we get colors that are in neither of the two input images. We realize that although some woods have slightly different greenish or reddish hues, it is better to only work on gray levels. And in fact, if we just match the intensity histograms, things look about as they should. To find good matches for a given patch, we're using a Euclidean distance on two feature channels, grayscale intensity and edges. This way we can match with a good balance between patch intensity and structure distributions. However, it turns out that, even in combination with histogram matching, does not automatically produce good-looking results. Rather, it leads to an output that fully utilizes the intensity gamut of the texture while destroying the gamut of the original target image. On the other hand, no matching at all doesn't work either. Here the target is brighter than most of the source, so we end up drawing only the brightest type of wood and end up with a parquetry that looks rather dull and flat. It seems that the truth is somewhere in the middle. A simple linear blend between full histogram matching and no matching at all reflects the contrast of both target and source quite nicely. So that's what we're going to use from here on. Let's look at some more of the challenges that come with such a pipeline. When working with wood or any other natural material, every piece is the only one of its kind, and when it's cut out and used, it's gone. We can't have another copy of it, even if we need it somewhere else. Respecting this constraint is fairly easy. In addition to the material texture, we need to keep track of a usage mask. Once a patch has been used, it is masked out from future use. So if we have a big enough supply of wood, we can cut pieces from it and keep going until we run out of material. We can even feed new wood plates along the way if needed. This greedy approach does a surprisingly good job. What's also clear, however, is that the order in which patches are drawn controls the quality of matches. Patches that get drawn later may no longer get the piece of wood that fits them best. Finding a globally optimal set of patches is exponentially complex, so that's not an option. However, we can devise heuristics to prioritize the selection of patches. An extremely simple rule is to start at the center and then work outward. Most target images are framed such that the most important things are happening in the central area. If this rule fails, we can prioritize our patch selection by visual saliency in the target image. This is not hard to do and feels like the right way, but it's not without risk. What might end up happening is that we have some parts in the target image that are really smooth. Following saliency as a measure for importance, those regions will be the last to be matched. So by the time we reach them, we might only have some strongly textured material left. These patches might have done less damage to the output image had they been used in a region that was more strongly textured to begin with. So we're operating in a design continuum. For this ablation test, where we produce copies of the same target picture from a limited supply of wood, a mixture of both strategies appears to work reasonably well. Note that this is an extreme example. Making multiple copies of the same target is always prone to problems, because then you know there is going to be competition for every patch. So the take-home point here is we want to go for a variety of different target images, and we want to always try to have enough material at hand so we can avoid the starvation scenario altogether. So far, we have not talked about the shape of our patches. We can approach this in different ways. The most basic way of segmenting the input image into patches is applying a regular grid. This results in a very blocky look that can resemble pixel art or 8-bit art. Since each patch is reconstructed from a single piece of wood veneer, the contrast of the reconstruction is limited by the intensity gamut of each individual wood type. Also, it is easier to find a piece of wood that satisfies a single intensity than to find one with a step edge between two given intensity levels. We can address this issue by placing patch boundaries on high contrast edges. To this end, we have developed a semi-automatic image segmentation pipeline. We start with a regular grid as before. The user then selects the edges that should fall onto patch boundaries and snaps mesh vertices to these edges. The output of this segmentation step can look like this. Note how the grid follows feature lines in the image. Some cells are cut in two to accommodate a diagonal feature. This is what the overall result looks like after matching all the patches. We can clearly see that the characteristics of the input image have been transported to the wood puzzle. The target image segmentation has a strong influence on the style of the finished parquetry, and it is one of the ways users can express artistic intent in our pipeline. By lowering the resolution, we generate a very basic, sketch-like result. By raising the resolution, on the other hand, we receive a very detailed rendition of the target image, where even fine image details like eyelashes are preserved. Besides these grid-based approaches, the method works equally well with hand-drawn artistic segmentations, here one with only a few dozen pieces, as well as posterizations, if we don't mind losing fabricability. For the details on how we assemble these technical components in our fabrication pipeline, please see the paper. Now, with everything in place, let's look at some results obtained using computational parquetry. Here we see two renditions of our cat using two types of wood. On the left, zebra wood, and on the right, maple. Maple has very limited contrast, so it takes some careful observation to see the cat at all. On the other hand, the intricate shading caused by the wood's anisotropic BRDF gives this parquetry a fascinating impression of depth. We already saw these two pieces. The left is an early attempt to get the fabrication process running. You can see that some of the veneer came off during assembly and finish. The right example uses coarser quad-like patches and is one out of a total of 7 images done in a series from a much larger material stock. Here they are. You can see that we distorted the grid slightly to follow the facial contours, but also to achieve a sense of focus on the face, while blurring out the periphery. Overall, it took us about 3 person-weeks to design, cut and assemble these 7 portraits. With further automation, it should not be too hard to further reduce this effort. We have set up an online gallery where these portraits can be inspected at full resolution. You can find it under this link. Computational parquetry is a novel fabrication technique that exploits the rich and varied structure of a natural material to craft detailed renditions of a given target image. Besides incorporating detailed solutions to many task-specific challenges, our pipeline also allows the user to express their artistic intent. Thank you.